So I'm just going to prove some results for some of the inverse trig functions. So the first one is that we're going to prove that y equals sine inverse x is an odd function. Now you might remember, to prove something is an odd function, we start by looking at f of negative x. So this is our f of x, same thing. So f of negative x would be sine inverse negative x. Now just for ease of this, I'm going to actually say y equals sine inverse negative x. And what we want to do to prove that it's an odd function, we want to prove, required to prove, that's what RTP is, required to prove that y is also equal to negative sine inverse of x. Okay, that's what we need to prove. Now, in order to do this, I'm going to take sine of each side. So sine y equals negative x. But we also have to keep in mind the range of this. So we have to say that the y then is going to be from negative pi on 2 to pi on 2. That's really important because as soon as we do that, this function has more results than that one does. This one is limited by its domain. So I'm just going to multiply each side by -1. I'm also going to turn it around at the same time. So I'm going to write x on the left. So the minus becomes negative sine y. Now we know that sine is an odd function. Okay, we know that already. So we know that that is equal to the sine of negative y. We've already proved that already. But also because negative y is in the fourth quadrant. Okay, and we get the same result there, but negative of. So sine of negative y in the fourth quadrant is the negative of sine of y in the first quadrant. Okay, that's what I mean by that. Now I'm just going to take sine inverse of each side, so I'm just going to reverse the process. So we're really just proving this by the fact that using that sine is an odd function, that works there, and that's still the fact that I've gone in the fourth quadrant, I'm still in this range for the y values. And let's take the negative of each side and turn it around. So, y equals negative sine inverse of x. So therefore it is an odd function. So that's that proof done. Proving that tan is an odd function is exactly the same, so you should pause the video and try and do this yourself first. So firstly I'm going to find f of negative x, which is tan inverse of negative x. I'm just going to rewrite it as y instead, just like I did above. And I'm just going to take the tan of each side, but I'm also going to note here that y has to be between negative pi on 2 and pi on 2, because that's our range defined by the fact that we're looking at the tan inverse function. Make it x equals, I'm multiplying by -1, negative tan y. Now the negative of tan y, I'm just going to explain this a little bit more. I did explain it above, but I think I was a bit brief with it. So we are stuck within this range of values here, from negative pi on 2 to positive pi on 2. So we're only looking in that area. Now tan of y, if this is y, is the result from this angle here, which is of course that over that. If I take the negative of that, because of our all stations to central, tan is negative down here. Note this proof wouldn't work for cos because cos is positive down here. So if this angle here is y, then that's like tan of negative y. I get the negative of what I get there because cos is positive here, tan is negative down here. So that equals tan of negative y. It equals tan of this angle. So the negative of this one equals the tan of that one. Okay, take tan inverse of each side again, equals negative y, multiply by -1 and turn it round. So y equals negative tan inverse of x. So therefore it is an odd function. So it really is this bit here that's key, the fact that sine and tan are odd functions, which is why they're both negative here when they're positive there. That's a key part of this proof. Okay, we do have a similar result for cos. Cos is not an odd function, so we can't show it's an odd function, but this is a result that does work. Cos inverse of negative x is equal to pi minus cos inverse of x. And the way we prove that is in exactly the same way. So I'm going to just write down y is cos inverse of negative x. So that's my left-hand side there. And I want to prove that y is equal to this also. So as before, the first thing I'm going to do is take cos of each side. So cos y equals negative x. But I am going to note my my range here. And for cos, remember, so sine and tan are both from negative pi on 2 to pi on 2. But for cos, it's 0 to pi. So what we're talking about in terms of the unit circle is that area there from 0 to pi. And those are the only things we can consider here when we've got y equals cos inverse. So let's multiply by -1 like before. So x equals negative cos y. So if I've got an angle here, that is y. Now, all stations, cos is negative over here. So the negative of this one would be the result there. It'd be this result. So cos of y is the negative of cos of pi minus y. Okay, if this is y, this one is pi minus y. So that actually equals positive cos of pi minus y, because the negative's up here. So these two are negatives of each other. This one it's positive, this one it's negative. Okay, let's turn that round. So pi minus y, taking cos inverse of each side, equals cos inverse of x. Now I'm just going to rearrange that to make y the subject. So I'm actually going to plus the y and minus the cos inverse. I'm actually going to turn it around again. So y, which is now over here, is pi minusing cos inverse of x. So that is our proof. We know that y was cos inverse of negative x, and we've just shown that it's also equal to pi minus cos inverse of x. Okay, now you could be asked to repeat any of these proofs. They're not on the reference sheet. They are something you would have to prove yourself. Okay, number 4, show that sine inverse x plus cos inverse x equals pi on 2. Now this result is one that I would strongly suggest you memorize. It comes up a lot and it's useful to use it, and you can just use it. Now we are going to prove it here. So I'm going to start by letting y, let's say let y equal sine inverse of x. I am going to take the sine of each side. So sine y equals x, but only when y is in that domain, negative pi on 2 to pi on 2. That's very important. Now, sine y, we know that sine and cosine are complementary ratios, trig ratios. So if this is y, this one up here is pi on 2 minus y. Remember, pi on 2 is 90 degrees, 90 minus y. And sine of y is equal to a over b. Cos of pi on 2 minus y is also equal to a over b. So that's actually equal to cos of pi on 2 minus y. Let's take cos inverse of each side here. I'll just write that x. So cos inverse of x is equal to pi on 2 minus y. Now, for that little bit there, we don't actually have to worry about the range, because we're not going from cos inverse to cos, we're going from cos to cos inverse. The range of this function is -1 to 1. It's this one that limits our domain, and going that way doesn't limit it in any way. Now, let's look at what happens when I add sine inverse and cos inverse. So sine inverse x plus cos inverse x, well, we originally said sine inverse x is equal to y. So sine inverse x is y plus, now cos inverse is pi on 2 minus y. So that's a really, really nice result. The y's cancel, pi on 2. So as I said, it is a nice one to memorize, just the result. You could be asked to redo the proof, so it's good to know that as well. So I'm just going to look at some ways you might use those results. So you might be asked to do this with specific numbers in it, but that proof was to do it algebraically, but here it is with specific numbers. And if you're asked to show that, it is perfectly acceptable just to say left-hand side equals sine inverse of -1. Now, you could draw the sine inverse curve to prove that. So we can see here with the curve that sine inverse of -1 is negative pi on 2. Now, if you haven't learnt the sine inverse curve, then you could also do that using just the normal sine curve. But you do need to remember to go from negative pi on 2 to pi on 2. Okay, so you want to know where does sine equal -1? And that's down here at negative pi on 2. It's a bit harder to do with the unit circle, remember, when it's 1 minus 1, that kind of thing. Now let's look at the right hand side. So negative of sine inverse of 1. So sine inverse of 1 up here is pi on 2, or here, where does sine equal 1? That's here on pi on 2, so that's negative pi on 2 either. Now that's very trivial. You are much more likely to see that with the cos rule, where you've got the pi minus going on. There is an example of that on page 648 in your textbook, example 26a, so you should have a look at that one too, but it's quite similar. And we should just say, therefore, left-hand side equals right-hand side. It would be okay to stop there, but I would also just write the result as well. That sine inverse -1 equals negative sine 1. Now you could get this with any number between -1 and 1. As long as this number is the negative of that one, it's the same result. Okay, and this one we're being asked to prove that sine inverse 3 on 7 plus cos inverse 3 on 7 equals pi on 2. Now we just saw that from a result in that proof. So I'm going to call this angle theta here, and we know that sine inverse of theta is equal to 3 on 7. So sine inverse of 3 on 7 is equal to theta. Sine of theta equals 3 over 7. Okay, now I'm going to call this angle up here alpha. So we know that sine inverse 3 on 7 is equal to theta. We know that's a right angle. And we know that cos inverse from that same triangle, 3 on 7 is equal to alpha. So therefore, if I add those, so sine inverse 3 on 7 plus cos inverse 3 on 7, I get theta plus alpha. Okay, now I'm just using radians here, so this angle here is pi on 2. And I know if I do pi on 2 plus theta plus alpha, that I'm going to get pi, or 180 degrees, minus pi on 2 from each side, then theta plus alpha equals pi on 2, and that's exactly what we've got here, pi on 2. Now, if these had been exact values, so like 1 on root 2, for example, or half, or root 3 on 2, or something like that, we could have literally just evaluated each of those to add them together, and we would have also got pi on 2 there. Okay, so we're looking at the inverse of an inverse trig function. So we're asked here to evaluate sine of sine inverse root 3 on 2. Now, sine and sine inverse cancel each other out, but you do have to be careful because of the limited domain and range of these things. Let's just evaluate this and see what we get here. So sine inverse of root 3 on 2 is pi on 3. So that's equal to sine of pi on 3. And of course, sine of pi on 3 equals root 3 on 2. So, hey presto, the sine and the sine inverse cancelled each other out. Okay, so let's try this one. Sine inverse sine 11 pi on 6. So firstly, we need to look at that 11 pi on 6. And that's down here. So this is 2 pi if I've gone all the way around. 2 pi is the same as 12 pi on 6. So 11 pi on 6 is just pi on 6 back down. So sine here by our all stations to central, because it is sine, this one is going to be negative. So this is going to be equal to sine inverse of negative, now looking up here at our triangle, pi on 6 is this one, so half, sine inverse negative half. Now we just saw before that that is equal to the negative sine inverse of half. If we look on this graph, it is going to be down here somewhere. So that's negative. So sine inverse of half using up here is going to be pi on 6, negative pi on 6. Now this time the sine and the sine inverse did not cancel each other out. And the reason for that is because this value is not between negative pi on 2 and pi on 2. Okay, so the range for this function is in there. So that's why this one didn't work. Okay, I've just written that down. So because sine is periodic and it happens over and over again, the results we get here may come back into this domain, so we can evaluate these things. But it doesn't mean that the sine and the sine inverse are necessarily going to cancel each other out. They always will if this is between negative pi on 2 and pi on 2. But if it's outside that, then they won't. Now, if we're evaluating the sine inverse first, then that already limits things down. If we're finding the sine inverse first, everything's already been limited down, and the result will actually always work. You'll always get that the sine and the sine inverse cancel each other out. But if the sine inverse is on the outside and we're finding the sine first, that's when we're going to have issues. That's when it's not always necessarily going to be the case that the sine and the sine inverse cancel each other out. So it depends which function is on the inside of the brackets. So here's a summary of when this works, but you can see it's fairly consistent. So sine inverse x, well, you can only work sine inverse x if the x is between -1 and 1. So we are limited to the x being between -1 and 1 for that to even work. And that's because the sine function never goes above 1 or below 1. So that's just a standard limiting thing on what sine inverse is, that we can only calculate it with x between -1 and 1, and that's the same for cos. For tan, x can be negative infinity to infinity. We can calculate tan inverse of any number, and that's because the range of the tan function, or the domain of the tan inverse function that goes that way, is negative infinity to infinity. So these three, we are limited by the domain of the function inside the brackets. And as long as we're within that domain, the sine and the sine inverse cancel out, the cos inverse cancel out, and the tan inverse cancel out. Now when we look at these ones, we're limited. So again, we're limited by the inverse functions here. We are limited by the range of the inverse functions here. So the range of sine inverse is between negative pi on 2 and pi on 2. So they're only going to cancel out there if this x causes them to if this x is within the that range of values for this function. Okay. If we're in that area, if we're in this area where this graph can be drawn, then it's all good, it works great. If we're not, then it doesn't. And that's true for all of these. If we're in the area where the inverse function can be drawn, domain or range-wise, then that's fine, we can evaluate anything. So for cos, same thing, from 0 to pi for cos, and tan, just like with sine, is from negative pi on 2 to pi on 2. I would suggest memorizing these ranges of values that work for the inverse trig functions. They're really important to remember.